Throughout human history, mankind has shared an innate trait. The desire to explore. Prehistoric men and women may have stood curiously at the opening to caves and wondered what was over the next hill. Ancient voyages sail to distant lands, risking hardships and even death in hopes of discovering a new place. The 20th century saw a massive transformation of humanity's exploration, which took the next logical step, venturing into outer space. There is no doubt that space exploration is one of the biggest achievements in human history. Unlike in many science fiction movies and TV shows, the space travel reality is far from the luxury spaceships such as the Star Trek franchise's USS Enterprise. Obviously, we can't use warp drives or teleporters to zip around the cosmos, and for the near future we are stuck with spaceflight that trundles through the void. For years, there have been many theories and ideas for interstellar travel. These include nuclear propulsion, ion drive engines, constant acceleration drive. The list goes on. So right now our rocket ships we're still using just what we call chemical energy, so very little has improved in our capacity to propel ourselves through space since for 100 years almost now. So there's been some talk about other kinds of drives. One of them is a solar sail, where you can use propulsion from sunlight that you open up a huge sail relative to the size of your craft so that you get maximum sort of pressure from sunlight, and that can accelerate you for free. And with the way you'd move around is you would attack just the way you would a sailboat. You would tack into the wind or away from the wind, but here the wind is sunlight that you're doing this with, and then you can navigate the solar system. It's a little slower, but maybe you would ship cargo that way and then send people faster. And so the future of space exploration need not be limited to chemical energy. There are other drives. There's a plasma drive, where you have very hot gas and you let very high-speed particles come out, because the hotter gases, the faster the particles move, and you let them come out. And that is a very low impulse propulsion. No, you're not going to sort of accelerate very much when one particle comes out, but this accumulates, and you can ultimately accelerate to very high speeds doing so now. So here's the problem with this and all these frontier means of propulsion. Yet you can go real fast with them. Instead of taking 9 months to get to Mars, you'll take a month. Perhaps if you want to go to visit Saturn, instead of taking 20 years, you'll take 2 years. But even if you got to the speed of light, near the speed of light, because you're not going to reach the speed of light near the speed of light you want to cross the galaxy, we'll watch you do this. By our time reckon, it'll take you 100,000 years. At the speed of light, by the way, you will age much more slowly, so you'll get there without much time having elapsed. But we who sent you will see you take 100,000 of our years to do that. And so this is not a realist. You come back, we would have all long forgotten about you. That's if civilization is still here. So none of these drives solve the interstellar travel problem relative to a human lifespan. If we lived a million years as individuals, sure, who cares if it takes 1,000 years to get somewhere? That's 1/1000th of your life. Sure, if it's a really interesting place worth going to. So what we really need is wormholes. Just you open a door here, and on the other side of the door, on the backside, you're in another part of the galaxy. Current technologies cannot grasp these ideas, and space travel will remain something that involves very long and exhausting journeys for the near future. Despite this, we as a species are driven to explore the unknown, discover new worlds, push the boundaries of our scientific and technical limits, and then push further the time in a close quarters with only 1 or 2 or 3 other people, months and months, and in some cases years. There's a whole psychological dimension to that. Can we remain emotionally stable over those times on Earth? People kill one another, they get into fights. There are many, even in the film Interstellar. There's an astronaut fight scene. So there's the fact that if you fly without creating artificial gravity, that you are weightless the whole time. Are you perpetually motion sick, or do you get used to it? And if you get used to it, are there any other factors on the body? Your body expects 1 gravity, 1 g, we call it, which is the equivalent of Earth's surface gravity through space. If you can create artificial gravity, good. If you can't, what is it like to be weightless for a year en route to your destination, or longer? We already know some of the answers to that. You begin to lose bone density. Other things they worry about: food. Not only is there enough food, but will you like the food? If you get bored with the food, will that affect your morale? And then you're less effective doing other tasks. Do you need comfort food? Do you want exotic food, international food? Is there enough water? Do you recycle the water? If you recycle the water, that means it collects all of your urine, filters it, and then you drink it back. Is that too freaky for you to do? Little things that we take for granted are not something that is normal when you are in space. There is a strong, fundamental interest in going back and studying the moon as well as exploring its minerals, water, and energy resources. The moon and Mars can be viewed as stepping stones on the way to becoming a spacefaring civilization able to thrive beyond Earth's orbit. Mars has a lot to offer. It is not only a fascinating place in its own right, but it will also become the stepping stone towards further exploration of our solar system. Curiosity and explanation are vital to the human spirit, and accepting the challenge of going deeper into space is the next natural step in human evolution. More than 50 years after the astronauts of Apollo 11 made their historic voyage to the moon, it is time to feed that spirit in a new generation and inspire the next great young scientists to follow in their footsteps. The red planet is ideal for human colonization and has been named as the most viable option for permanent colonization in our solar system, but the many aspects of human space exploration are inherently interrelated and go beyond simply launching spacecraft into orbit or landing astronauts on another planet. A large proportion of current research into space is involved in understanding how to keep humans alive when a spacecraft built for humans ventures into deep space. It requires an array of features to keep it and the crew inside safe. Both distance and duration demand that spacecraft must have systems that can reliably operate far from home, be capable of keeping astronauts alive in case of emergencies, and still be light enough that a rocket can launch it. So if we want to send a spacecraft all the way to Mars, first we will need a fast rocket to escape the pull of Earth's gravity. The heavier the spacecraft, the more powerful the rocket needs to be to lift off. You have to leave when Mars and Earth are properly aligned. So just to remind people, if you see Mars in the sky and you start traveling to it, you have to travel to where Mars will be when you get there. So it's a matching of trajectories that matters here, and so what we call the minimum energy trajectory. So it's one where you burn your engines and then you shut them off, then you coast to Mars until Mars pulls you into its gravitational influence, and then you fall towards Mars. That takes about 9 months, but if you run your engines the whole time, which we can't do yet because we don't know how, because we don't have enough fuel. If we have filling stations along the way, you could do this. You fill up, burn your engines, and then you're accelerating to Mars. By the way, that will give you gravity, artificial gravity, inside the ship if the ship is accelerating, and then, but to slow down, you have to turn the ship around and then accelerate to slow down. But anyway, if you do that, you get to Mars in weeks, a few weeks, but it'll take a boatload of fuel to do that. But if fuel is cheap, then why not just need filling stations? According to NASA, a one-way trip to Mars would take about 9 months if you wanted to make it a round trip. All in all, it would take about 21 months, as you'll need to wait about 3 months on Mars to make sure Earth and Mars are in a suitable location to make the trip back home. Through addressing the challenges related to human space exploration, we expand technology, create jobs, and encourage innovation. We are inspired by the successes of our technological processes on Earth and beyond. The knowledge we gain will have a transformative effect on life on Earth and help us to strengthen our economy, all while furthering space exploration and the desire to understand our place in the universe. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this. Music. You once we've gathered enough speed around Gargantua, we use Lander 1 and Ranger 2 is rocket boosters to push us out of the black holes of gravity. Imagine light leaving the first stars and galaxies nearly 13.6 billion years ago and traveling through space and time to reach us. Music. Imagine a fundamental theory in physics that provides a description of the physical properties of nature and the scale of atoms and subatomic particles. It is astonishing to think how modern physics of the 20th century has unveiled some of the deepest mysteries of the cosmos, and yet again we may be on the verge of discovering the mechanisms that explain in great detail our universe and our place in it. Look at the observable universe, which is the piece of the universe and beyond indeed that we are claiming to understand and are indeed understanding in detail, and you realize that maps like this show you there are 350 billion large galaxies in the observable universe, which is 90 billion light years across, and we claim to understand how all that interacts, what it's made of, and indeed where it came from, and I think the size of our quest, the almost hubristic nature becomes quite obvious. And the numbers are really quite ridiculous. The universe is big, I suppose, is what I'm trying to say, as well as understanding a map and the size and scale of it. We understand, of course, in some great detail, the evolution of it, from very close to the Big Bang. The fact that we can even talk about numbers like 10 to the minus 43 seconds after the Big Bang is remarkable. Of course, that number comes from the Planck scale, which comes from the weakness of gravity. There are 4 forces that we know of in the universe. Gravity is by far the weakest one of the great mysteries, is why gravity is so weak. So we talk about numbers like that. We then have the beginnings of experimental data when we start to talk about the time period from 10 to the minus 36. To avoid a 10 to the minus 32 seconds, that's the period when we think the universe went through an exponential period of expansion, increased in size by a factor of 10 to the 78, less than the blink of an eye. The reason I say we have experimental data in principle is that certainly the measurements of the cosmic microwave background fit in with that theoretical statement. The idea that that's the way that physics was there was that exponential expansion back then certainly not proven by any sense, and the mechanism, of course, is not understood, but the fact that we have a window now with precision cosmology for the first time on those eras is, I find, quite remarkable. In order to fully understand what makes the universe tick, we have to be able to grasp its early stages and the universe's subsequent evolution. The earliest stages of the universe's existence are estimated as taking place 13.8 billion years ago, with an uncertainty of around 21 million years in the very early universe. The subnuclear particles that later made up the protons and neutrons existed in a free state as a quark-Coulomb plasma. As the universe expanded and cooled, the quark-Coulomb plasma would undergo a phase transition and become confined into the protons and neutrons we know and love today. Cosmologists can give us a glimpse of the early universe way before nuclear synthesis begins. Enter the Planck epoch. The Big Bang occurs, in which ordinary space and time develop out of a primeval state. During the Planck epoch, cosmology and physics are assumed to have been dominated by the quantum effects of gravity, but we have yet to develop a theory of quantum gravity in physical cosmology, assuming that nature is described by grand unified theory. The grand unification epoch was the period in the evolution of the early universe following the Planck keyboard, in which the 3 forces of the Standard Model are still unified. According to inflation theory, the inflationary epoch was the period in the evolution of the early universe when the universe underwent an extremely rapid exponential expansion. The rapid expansion increased the linear dimensions of the early universe by a factor of at least 10 to the 26 power. The electro-weak epoch was the period in the evolution of the early universe when the temperature of the universe had fallen enough that the strong force separated from the electro-weak interaction, but was high enough for electromagnetism and the weak interaction to remain merged into a single electro-weak interaction above the critical temperature. For electro-weak symmetry breaking, the quark epoch was the period in the evolution of the early universe when the fundamental interactions of gravitation, electromagnetism, the strong interaction, and the weak interaction had taken their present forms, but the temperature of the universe was still too high to allow quarks to bind together to form hadrons. The quark epoch began approximately 10 to the minus 12 seconds after the Big Bang. During the quark epoch, the universe was filled with a dense hot quark-Coulomb plasma containing quarks, leptons, and other antiparticles. The following period, when quarks became confined within hadrons, is known as the hadron epoch. This started 20 microseconds after the Big Bang. The hadron epoch is mostly characterized when quarks are bound into hadrons, and slight matter-antimatter asymmetry from the earlier phases results in an elimination of antibarons. This symmetry breaking is one of the greatest mysteries of the universe and the reason why we exist. What was it that caused that symmetry breaking? When did it happen, and what are the details of that symmetry breaking? But of course then, when you move to 10 to the minus 10 seconds, a billionth of a second after the Big Bang, so then we're in firm experimental territory that absolutely is the energy range of the LHC. So we have a very firm, I think that's one of those things that when you think about it for a moment, it's quite remarkable that we have experimental data that tells us about the universe, the physics of the universe, as it was less than a billionth of a second after the Big Bang, then we move on to nucleosynthesis, the fact that we can calculate with high precision the ratios of hydrogen, helium, in particular deuterium, lithium, in the early universe. NASA's James Webb Telescope will use quasars to unlock the secrets of the early universe. Quasars are high-energetic bursts of very bright light from distant and active supermassive black holes that are millions to billions of times the mass of the Sun, typically located at the centers of galaxies. They feed on infilling matter and unleash fantastic torrents of radiation. Among the brightest objects in the universe, the quasar's light outshines that of all the stars in its host galaxy combined, and its jets and winds shape the galaxy in which it resides. Webb will gaze on 6 of the most distant and luminous quasars. It will study the properties of these quasars and their host galaxies and how they are interconnected during the first stages of galaxy evolution in the very early universe. It is fascinating to think how far the boundaries of ignorance have been pushed by physical cosmology. 20th century science was dominated by the discoveries of modern physics. It stands to reason the 21st century will also be triumphant for cosmologists. Even in 1897, the importance of the beginnings of particle physics, the discovery of radioactivity, was recognized. In fact, if you then look back from the point of view of the 1920s, this is an era, 20 years, part of a scientific lifetime when we get very quickly the radioactivity, we get quantum theory, we get relativity, the foundations of modern physics. And I found another remarkable quote, actually from Ernest Rutherford from Pisces book. It's a wonderful book if you haven't read it, looking back in 1924. So this is really, 25 years after the beginnings of modern particle physics. Rutherford wrote, the year 1896 marked the beginning of what has been actually termed the heroic age of physical science. Never before in the history of physics, as they've been witnessed, such a period of intense activity when discoveries of fundamental importance have followed one another with such bewildering rapidity. That's looking back at that period, the turn of the 20th century. I actually genuinely think, and I wonder whether many of us do, that we're living through the beginnings of such a period now. The level of precision with which we understand the universe at some level is quite remarkable, but also the number of experimental results now that are beginning to say that there needs to be a real shift in our understanding are also building up one after the other. We've seen of course dark matter. We're looking at things like the hierarchy problem, dark energy. Of course, all those results seem to point to a revolution in our understanding of the universe because of the experimental data that we are gathering in both cosmology on the larger scales and in particle physics at smallest scales. We have covered a lot in the early stages of the universe's evolution, but we still have a long way to go, including the epoch of neutrino decoupling, the lepton epoch, Big Bang, nuclear synthesis, photon epoch, recombination, the Dark Ages, star and galaxy formation and evolution, reionization, and finally the present time. We will do them justice and cover them extensively in another video. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this. Music you